We're going to start with clicker questions. So here's your first question. Why do we see phases of the moon?
Because of the weight of the shadow reflects the sun.
Oh, yeah, I got
So the broken chair?
No, the broken one's in my office.
Oh, can I put you?
Thank you.
Why? Can you wait a second? My phone was off. I can't even read these on here. Phone, turn on. We're still later.
You can zoom in.
But it's like off. Yeah.
Are you gonna sing today? Can you sing this song? I just thought you were singing this song. Oh my goodness.
Yeah, turn on. 4 more seconds.
Okay.
1 sec, please.
Haley and Justin. Okay, everybody's answered. We had 0, 0, 2, 3, and 13. So, okay, not that person. Eric, what's your answer and give us some reasoning?
I answered E.
D is in dog?
No, E.
E is in everyone?
Yeah.
Okay, and what was your reasoning?
We just talked about it like a couple days in a row in class.
We talked about it a couple days ago in class. Okay, on Wednesday. Yeah, Wednesday. So, what's causing a shadow?
Just causing the shadow.
Brandon, since you did the demo, what's causing the shadow?
The sun?
Okay, the sun is casting the light.
Like what's making the shadow?
Yeah.
Right?
The moon. That's right. It's the moon is casting a shadow. Only the side that's facing the sun gets hit by light. The other side is blocked by the moon. So it's the moon blocking the light that makes it so we see a shadow. And that's what causes the phases. Next question. During the time of a new moon, which of these geometries is true? A new moon is when the moon is dark.
I choose A.
Okay, we had nobody that chose A. Why did you not choose A?
Because we would be dead. It's not right.
Because there ain't no way the sun's ever going to get between the two of us.
Yeah, we
Okay,
tried.
so Candace, which one did you answer? Because we had a pretty even split there.
I answered C because isn't it when the moon is going around the earth and it's on the opposite side of the sun? So the earth is between the sun and the moon.
Okay, this is the alignment that causes a lunar eclipse. When the shadow of the earth falls on the moon. But as per the previous question, the phases of the moon are caused by the shadow of the moon. And so if we're going to see the side of the moon that's in shadow from itself, we have to be on the opposite side from the sun. So we have to have the sun, and then the moon, and then the earth, so that the sunlight is lighting up this side of the moon, and we're seeing the other side. Now, what kind of eclipse would occur in that situation? Everyone, not just Candace.
Solar.
Okay, so that would be a solar eclipse. A solar eclipse is when the moon passes in front of us, blocking the sunlight. Why don't we have a solar eclipse every time there's a new moon? And Brandon answered this.
Because we're rotating, so it has to be when we're, right?
It's not because, now, your answer has some reasoning to it. That is, the solar eclipses are only seen in small parts of the earth because we're rotating. You have to be where the shadow is hitting. But what was the reason why there's not some place on earth that has an eclipse every time we have a new moon?
Well, I think it's because like the moon isn't like always like in front of the earth. Like it's oftentimes like above or below. So like it doesn't get.
That is absolutely right. The moon's orbit is tilted about 5 degrees from the Earth's orbit around the sun. So most of the time, the moon is either above or below, being directly between us. So it's not a perfect new moon because it's not directly between us. If it was directly between us, it'd be a perfect new moon / eclipse. Now, how many people have seen the movie Apocalypto? Wow, really? Not a one of you. Well, I still have to mock Mel Gibson. In the movie Apocalypto, they are sacrificing humans to the gods because the sun is being taken away by the gods. What was going on? A solar eclipse. So they are sacrificing these people. They're chopping their heads off one after the other. And finally, the sun starts returning. Hooray! They have appeased the gods. This is a very common theme around the world and cultures. Pretty much the people who know what's going on know that eclipses are coming and they know how they behave. The people who don't know, they tell them it's about the gods and we're going to appease the gods. So then, what do they do with the people who they haven't killed yet? They don't need to appease the gods anymore, so they let them go, but they decide to have sport with them, and so they're like shooting at them with arrows, and our hero in Apocalypto escapes them. And they keep hunting him because, hey, it's a challenge. This guy's a good one. And during that night, what phase should the moon have been?
Full moon.
If the moon is between the earth and the sun for solar eclipse, what phase is it in? It's a new moon. And yet in the movie, it's a full moon because they failed on the science front. So, not truly to mock Mel Gibson, but to point out that, these kinds of things, they're reasonably logical, but a lot of people simply don't pay attention and text on their phones instead. So, observing the sky. Going out at night and looking at the sky is one of the enjoyable things in life. When I teach astronomy, one of my goals is for people to be able to go out with a person and impress them and, have a good date by pointing out things in the sky. So when we look in the sky, we see pictures. These pictures are connect the dot pictures that people have contrived over time and that we've learned to recognize. So an example here is Ursa Major. Ursa is bear, so Ursa Major is the big bear. Virtually no one recognizes Ursa Major. All right, Ursa Major, it's got hind legs, front leg, head out here. What do you recognize? The Big Dipper. The Big Dipper is called an asterism. The Big Dipper is this connect the dot picture right here. Compared to Ursa Major, that's just a tiny fraction of the constellation. Now, originally, constellations were pictograms in the sky. So people looked up there and they made stories about their gods or things that were important to them. So we have most of our constellations, roughly half of them, are related to people's ancient stories about things in the sky. And what people? Do you suppose it was limited to just a certain people who were looking up in the sky and making pictures? Probably everybody. So the American Indians have their constellations, their pictograms. The Chinese have their constellations, their pictograms. but they're not the ones we use because the motion of science through time has been going from Greece to the Middle East, to Arabic scholars, and back to Roman scholars. And the names we have are based on who were the preeminent scholars, but our chain stays in that region. So we have a lot of stars that have Arabic names because the Arabic scholars were the preeminent scholars of their day. Our constellations actually have Latin names, but they're based on, like Greek and Roman mythology. Of course, Ursa Major is not a mythological creature, but you have things like talking about Cepheus, the king of Ethiopia, and Cassiopeia, his wife, and Perseus, who comes and rescues their daughter Andromeda, that the oracle of Delphi had told them to sacrifice to Neptune. These convoluted stories, and they make picture stories in the sky. So that's the origin of constellations. Today, scientists have made constellations much less exciting. Today, constellations are areas in the sky. So this picture of the bear is now a fanciful picture that goes with an area that shapes something like, I think it's something like that. Okay, it's deformed. It doesn't stick out that far. But it's something, it doesn't look like the bear, but it's an area in the sky. And every star that's in that area is considered one of the stars of Ursa Major, even if it's not part of any part of the picture you see. So scientists have moved the word constellation to mean an area in the sky. There's a total of 88 of those areas in the sky. But when you go out and you're looking at things, when you're looking at, let's say, Cygnus, when you look at Cygnus, you're probably going to see something like this. Well, that is called an asterism if you just connect the dots and say, hey, I see a cross. It's an asterism. It's a connected dot picture. And Cygnus the swan has additional pieces to the wings, and the actual area for the constellation is something like that. So the green is the actual constellation. The swan, you can make out a swan with the stars there, the bright stars, and then you have the asterism of the cross. I always like to point out that this star here is the butt of the swan. That's actually what it means, I am told. I don't speak Arabic. It's Deneb. So, constellations, you should know what they are. We have a certain set of constellations that fall on the ecliptic. Ecliptic is the name for the path that we see the sun as we travel around it. Now, I said that correctly. What we usually say is the path that the sun takes as it goes around the earth. What's wrong with that? Yeah, the sun's not going around the earth. The earth is going around the sun. But as we go around the sun, it appears to us like the sun is going around us. And even though we can't see the stars during the daytime when the sun's out, because the sun is overpowering their light, we can map out where the sun would appear, and that path is called the ecliptic. And there is a band about 18 degrees north and south that's called the zodiac. What does the zodiac mean? No answers? It's not something bad. It's the zoo. It's the collection of constellations. They're all animals that are there roughly on the ecliptic. It's the constellations that the sun is seen to pass through as we view it from Earth. So the zodiac constellations, there's nothing wrong with them. They're just the constellations that are on that path. And so I was born in the very middle of November. And where was the sun as viewed from Earth when I was born? Anybody know? Okay, let's take another shot. Anybody know my sign of the zodiac, being born middle of November? I am a Scorpio. And so one would assume that the sun was in the constellation Scorpius, the scorpion. But one would assume incorrectly. Now, first, let's start with astrology is not a science. Astrology is taking scientific information. Where do we see the sun in the sky? That's scientific information. And drawing from that a non-scientific conclusion that my life is going to be affected by where the sun was when I was born. Actually, we know it's where the earth was, right? So, remember, scientific hypotheses have to be based on scientific ideas and make measurable predictions. It's failing on those. It's not based on scientific ideas. They have scientific measurements, but it's not, that it affects my life is not based on scientific ideas. Furthermore, how many days are in a year? 365-ish. The correct answer is 365.2422 days per year. It's not an integer number. Because it's not an integer number, we have to do something to correct the calendar. So what do we do to correct the calendar? We add a leap day. How often? Every 4 years. Now, that is what the Julian calendar, the calendar of Julius Caesar, did. It added a leap day every 4 years. But if you add a leap day every 4 years, on average, you're adding 1 out of 4. What's 1 divided by 4? 0.25. So on average for the Julian calendar, it was 365.25 days per calendar year. Now that's pretty close, right? But roughly every 100 years, you're going to get off by a day. And so over time, the new year kept moving. And so scientists, a long time ago obviously, realized this will never do. We're going to end up having summer start in July if we don't do something. And so we have a different calendar that we use today that's the Gregorian calendar. And probably all of you except for Brittany are like, I thought we had a leap year every 4 years. But that's not what the Gregorian calendar does. The Gregorian has a leap year every 4 years, add a leap day every 4 years, except if the year is divisible by 100. If it's divisible by 100, you don't have leap year. And now all of you are astute enough to know that 2000 was in the recent past. Was that a leap year? It turns out it was. Because there's another rule. Because if you just took out 1 every 100 years, 1 divided by 100 is 0.01, and you would drop down to exactly 365.24, which is closer to 365.2422, but not exact. And so every year that's divisible by 400, every year that's divisible by 400, you put the leap day back in. So that's adding 0.0025 back in. So with the Gregorian calendar, you have 365 plus 0.25 minus 0.01 plus 0.0025 is equal to 365.2425 days per year. It's not perfect, right? Still not 2422. But because things like when you have a major earthquake and you have a piece of the Earth's crust might move down by 2 meters, it's just like when I'm spinning around, if I pull my hands in, what happens to my rotation rate? I speed up. And so it actually changes the length of a day. And so because of that, the variation of the length of a day is in this digit, and they figure that's close enough. So that's what we have with the Gregorian calendar. That's what's different. This was instituted back around the time of Isaac Newton. And when they instituted, they said, well, we need to correct the calendar for the drift that's occurred since the Julian calendar was instituted. So depending on where you were on Earth, you went to bed one day and you woke up 10 or 11 days later because they just shifted the calendar on you. Now, the day of the week stayed the same. As a Seventh-day Adventist, it's kind of important to me that I worship on the seventh day, keep that Sabbath holy. They did not change. You didn't go to bed on Tuesday and wake up on Friday. But the day on the calendar changed to try to bring it back. Where's that all come from with this? The sun is in the middle of the constellation Libra on the day I was born. Because the calendar shifted by 10 or 11 days, but the signs of the zodiac, they just kept them fixed. Because after all, they don't mean anything, right? Now, the true believer says, oh, yes, but we've shifted the meanings, we've shifted the predictions to adjust for the shift in the calendar. Sure. If you want to say that, you can. Moving on. The Earth rotates. How do we know the Earth rotates? One thing you can do is you can just go out and observe the sky and look at what's straight overhead. Then look around for a while. You're out there with your honey, talk, whatever you do. And then an hour later, look at what's overhead. It won't be the same thing. It will have moved. What does that mean? Either the sky is moving. That's what this model was, saying that the Earth was stationary, everything was going around it, or the Earth had to rotate. So you can do that, and in the northern hemisphere, you're going to see all the stars rotating around the pole star, which we call Polaris, which is at the end of the Little Dipper. If you go to the southern hemisphere, I think I have a picture from the southern hemisphere as well. Nope, don't. If you go to the southern hemisphere, you'll see the stars going around an empty point. But you have two places on Earth where you can see the stars going around a point. What does this suggest for the shape of the Earth? Well, three-dimensionally, it's a sphere. Right? These things, it's really hard to understand how people can believe in a flat Earth when you have these two spots, where you can see, there's a center of rotation. And so you've probably seen really cool pictures like this, where somebody has just set up a camera and they have an exposure that went for like 15 minutes. And you can see the arcs caused by the Earth rotating over the time of the exposure. So in this picture, we can say, aha, north must be somewhere right about there. Assuming this is in the northern hemisphere. I can't tell north from south when I'm looking at this picture. Now, where are the stars? Once again, going back to the celestial sphere idea. The celestial sphere idea said that the stars are all on a single sphere, the same distance away from us. This is what Aristotle said. He said that you have out there a big sphere made out of crystal. Why a sphere? Because Aristotle thought that spheres were the perfect shape. Why made out of crystal? Because Aristotle thought that a quartz crystal was the perfect material. And Aristotle posited that everything out there was perfect. Only here on Earth do we have imperfections like people killing other people. So he said that we must have this perfect sphere with just the stars on it, with the points of light. Didn't know what they were, just the points of light. From measurements that we can make today, we know that the distances to the stars are very different. So these are the stars that make up the Big Dipper. So you have Alkaid, Mizar, that's not how you spell Eliath. Megrez, Vad, Merak, Dubi. Now what you notice is these names are all in Arabic. Why? Because they were the great scholars. There's another star right here above Mizar that's called Alcor. And Alkaid and Alcor actually have the same name originally. They're the rider riding on the horse Mizar. Different people couldn't agree on which one was the rider for the horse. So we look at those stars and they have numbers next to them. LY means light year. A light year is the distance light travels in 1 year. It's a very large distance. For reference, the sun is 8 light minutes away. So 8 minutes compared to a year, that's the same as distance from the sun to a light year. And you can see that the distances are vastly different. Alioth is way far away, whereas Megrez is comparatively very close. More than or less than 1/6 the distance away. Got a question?
So like, do you know why we see like some stars like brighter than others?
Absolutely, and Larissa's going to explain that to you.
Oh, fun.
Aren't you, Larissa? Yeah. So, and we are ready for Larissa, so come on up.
Okay. Woo. This is more student participation. That was the smoothest transition.
Okay, yeah. It was well timed, that question. So I am going to raise this, change to her picture she wants. That one.
Okay.
And, oh, come on, make it bigger. You see my F5 button here somewhere.
Should we do that part first? Or do it
Well, it's up to you. You do what
Okay.
you want.
So basically, we're going to talk about like applying the concepts of frequency, and luminosity, and color to how we view the stars. So do you guys remember when we used these fun little glasses and we looked at this and we looked at brightness and stuff? So now we're just going to relay that. So basically, we have like 2 equations that we're going to be using. The first one is about brightness and luminosity. Oh, which he has up here already.
Yeah, but I have the lights on so they can't read it.
Okay, should we do the glasses thing first? Yes.
It's your game.
Okay, so put on your little glasses. Is this on? Oh, on. So does everyone have glasses on? And I want you to tell me what you see as we turn this up. What difference do you see in your glasses as it goes from darker to brighter? I guess that kind of gives it away.
Well, there's the 2 things.
It goes from darker to brighter.
It goes from darker to brighter.
Colors once so pretty sides.
What did you say, Casey?
Much intensity of the coloration.
Right. Oh no, now I can't see my note. So basically, we're going to talk in this first equation about how the light that's given off is related to temperature. So right now we have it on this low voltage one, but when we make it hotter, what is the change in brightness? This is pretty obvious. Obviously, as we make it hotter, it gets
Brighter.
brighter, right? And so that's something called luminosity. And we have a little equation for that, so we can turn on the lights and we can go through the different stuff. So this is the luminosity equation. So basically we have this L. And so we're trying to find out about like peak luminosity is what it's called. So we have L. This is what we're looking for. A, this is area for a sphere. And Dr. Webb really nicely wrote out area for a sphere is 4 pi r squared. So in this case, R stands for, do you guys know? Radius, right. So when we have a bigger radius, we're going to have, wait, where is it? Right, so when you have a bigger radius or like a bigger star, it's obviously going to be a little bit, just like that, it's going to be hotter and it's going to be brighter. And then
The radius is only bright.
So what?
The radius is just going to make it brighter now.
Yeah, sorry. Make it brighter. So the E, this is just like a script E. It's like efficiency. And Dr. Webb was telling me yesterday that there's a scale from like 0 to 1, correct me if I'm wrong, 0 to 1 on efficiency. And in this case, stars are mostly always going to be 1s. So that's kind of another constant. And then this T stands for temperature, which is kind of what we're trying to figure out. Notice that it's temperature to the 4th power. So when you double this temperature, you're not just doubling it by a little bit. As you can see, it's going up by a lot. When we double it, it's going to be to the 16th. So it's really getting a lot hotter.
So now the direct answer to Brandon's question, she's given us the pieces. You have 2 things that are going to affect, well, there's a third thing that we're not talking about, distance. Right, so these 2 here, the bigger the star is, the brighter it's going to be. And the hotter it is, the brighter it's going to be. So those 2 things play into how bright it is. Then you have distance. If something's farther away, you know from practical experience, a car that's a mile away, you can just barely see its headlights. And if the car is 10 feet away, the headlights are blinding. The light intensity drops off with 1 over the distance squared. So if a car is twice as far away, it's 1/4 as bright. So that's the third thing that has to do with how bright you see a star. It's the distance, the radius, and the temperature.
Okay, so then for the second formula we're looking at, this is a lambda, and it's talking about this peak wavelength. And so it's like the lambda peak wavelength equals 2.9 times 10 to the 6. I forgot. Nanometers. This is a constant also. And then this T, again, is divided by temperature. So this one is kind of talking about Wien's law. It's talking about how objects at different temperatures emit spectra that peak at different wavelengths. So there's this little chart that's really helpful. So basically, this is showing that we have blue and we have red wavelengths, and the red ones, let me get this right. The red ones are not as hot, but our blue ones are the hottest, and they have the longer wavelengths. And the short wavelengths are the red ones, and they're a little bit cooler. Oh! The blue ones have the shorter wavelengths, and the red ones have the longer wavelengths. And so we were talking yesterday, and it's interesting because like our society associates like red with being like really hot, but actually the blue ones are hotter because we think about like UV rays and all of that has this blue lighting. So Orion, sorry, thank you. So you guys know Orion, like it's one of the most like common constellations on here. Way at the top we have Betelgeuse, and so based on what we just learned, is that red? Is that hotter or is it cooler? Cooler, and you can see that with the naked eye, which is really cool. And then there's this little nugget down here, Rigel, and it is really blue, like it's super blue. I mean, I guess these ones are too, but this one is going to have the shorter wavelength, and it's going to be a lot hotter, and that's really cool because you can see that. Yeah. Is there any more on that?
While she has this picture up, let's point out this right here. What is this?
Star.
Yes.
Wow, we're pretty good at this.
Yeah.
For the most part, we were right, but not for what I was actually hoping to get to. That's a star, that's a star. What's this? It's a nebula. It's a cloud of gas. It's a cloud of gas where you can see there's a different color to it. Do you see there's a different color?
Yeah.
Here's that color.
Whoa. Did you see something green?
Nothing.
I wish these things go.
Now, if you look at that color, go ahead. This is still part of her.
Oh, so we're just like wondering what color you guys see. What do you see right now? Because I can't see. I should get on glasses so I can see what they see.
Here's one.
Oh, thank you.
The glasses aren't very
So do you see how you see that one color in the middle and then one's coming out from it?
Yeah.
So right now it looks like it's on a lower temperature because you can see that red, right?
Yeah.
Do you see blue in it?
No.
So like there's not
No?
a ton of blue. There's a little bit of blue.
You should totally see blue.
I see blue,
but it's not.
Oh,
Is that like the brightest color that you guys are seeing? What's the brightest color that you're seeing? Don't look at it.
Oh, red.
You're seeing that red. So then as we turn it up,
Oh, we don't turn this up. This is a gas.
just kidding.
See, the color there is pink. Just like the color there in the center of the dagger of Orion is a pinkish color because it's the same gas.
Right.
So how do scientists identify what type of gas that is?
Okay, I know this part really well. So basically, each stars have these absorptions of frequencies, or frequency absorptions.
And if it's a nebula like this, it's emission instead of absorption. The stars have absorptions, like she was saying.
Yeah.
We didn't go over this part, so we only went over the absorption of the stars.
Yeah.
But this here is emission. Everything else is still right.
Okay, so like there's certain frequencies that are going to be absorbed. So like in hydrogen, which is one of the strongest, the colors that you see are kind of what's left over after it's absorbed. You said not in that case. Though,
Well,
because
this
it's
here is
absorbed.
just the reverse. So the colors you're seeing are the ones that emitted would be the same as the colors absorbed in the atmosphere of a star.
Right. So what's being absorbed is what you can't see. So there's distinct atoms that have these different frequencies, and you can kind of tell the temperature of a star by seeing how strong these absorptions are, and you can tell their composition, like hydrogen being the strongest.
So by the fact that we have this emission coming from this region, we know that it's a lot of hydrogen gas. And so this is a region where we have a lot of gas, and there are a lot of really young, super hot stars that are lighting up that gas. And so it's a place where stars are being formed. It's a star nursery. And so that's really exciting to scientists, having a place where they can look and find stars in the process of being created. Okay, I think that's what we had lined up.
Yeah, you can just tell about the temperature of stars by looking at what's absorbed, how bright they are, and you can see their temperature.
Thank you.
Yeah.
And then getting back, hit the button. Okay. I hit the button, it was already on, so I turned it off. That's my mistake. Okay, getting back to where we were in the lecture. Is your question answered, Brandon?
Yeah.
Okay, so we had two things going on. One, the temperature affects the peak radiation. Second, the temperature affects the total amount of light. So by looking at the color, you can get an idea of the temperature, and that also tells us about the light. So based on what Larissa taught you, which of these stars would be the hottest? Ready for Brittany, Tiffany, Candace, and Haley. Well, now just Brittany, Candace, and Haley. The sun will come out. Okay, I'm going to move on because we can't wait. I've got to leave things up to, once again, my assistant in a few seconds. So we had a very large contingent that said blue. Who said violet? Who said violet? No one's going to admit to it?
Can you just look it up?
It would take me a while. I can eventually look it up. I did look up the two people who said that the Earth had no moon. Violet would be the brightest, or not the brightest, the hottest. Because we talk about the spectrum going.
Question for you. Sorry. Okay, so I was torn with my answer because violet, isn't that a combination of red and blue?
No, magenta is a combination of red and blue. They look pretty much the same. I know. I'm happy with that. This is a kind of a technicality because usually we just say blue.
So you tricked us.
I didn't put it on a test, right? But the point here is to point out a technicality that violet is technically a shorter wavelength than blue. Violet and magenta look about the same to our eyes, but they're completely different colors, right? Magenta is a combination of red and blue. Violet is even shorter wavelengths than blue. And violet's kind of hard for our eyes to see, but it's the shortest wavelength that is visible, and so that makes it the hottest. Should be the only question. One question. Fail it, you fail the test. No. Even worse. All right. The second equation that Larissa went over was that luminosity, the amount of light given off, is highly dependent on the temperature as well as on the size. So bigger stars give off more light, smaller stars give off less light. If we look at the picture, I'll get you, Brandon. Actually, I have to stop right after going back to this picture. So what's your question?
What did the O symbol equal?
The O symbol?
Next to the area,
Oh, that's sigma. That's the Stefan Boltzmann constant. So it's a constant. It's a number, is what Larissa said, I think. If we look at this picture here, we have a very bright blue star and a very bright red star. A red star might be half the temperature of a blue star. If it's half the temperature, how does the amount of light given off compare per unit area? Temperature to the fourth power. So what's 1/2 to the fourth power? One 1/16. So the orange one is giving off about 1/16 of the light per unit area. How can it be as bright as the blue one?
It's closer.
Could be closer, could be bigger. And it's going to be always a combination of those. You have to do some more study to know which one it is. But Betelgeuse is what we call a red giant. It's a huge star in its dying stages. Because it's so huge, it gives off an enormous amount of light, even though it's not hot. Rigel is, well, it's a blue giant, not nearly as big, but very, very hot. Okay, it is time for the teacher evaluation. So I am just going to unplug and walk out, and